Einstein's theory of special relativity is perhaps the deepest and the most profound achievement of 20th century physics. And it's all the work of one man, Albert Einstein, who in the year 1905 wrote 5 papers at the age of 24 that changed the nature of physics. These papers dealt with the nature of space and time and their relation to electromagnetism. In spite of it being so important, the theory of special relativity actually is very simple. It does not require advanced mathematics, and in these lectures, I will help you learn this beautiful theory. All you might need is a little bit of calculus, at least at the very beginning. But first, why do you need the theory of special relativity? It's not something that one experiences in our daily life because objects move slowly compared to the speed of light, I mean. And therefore, even for rocket travel, it's not necessary. But when you have electrons and subatomic particles moving very, very fast, then it's absolutely essential. Why the word relativity? That's because all motion is relative. Let's understand this point first. Let's call the person who's running towards the right A, the person who's standing still with respect to the ground B, and this woman who's running towards the left C. So A is running towards B, let's say at 4 meters per second. And what that means is that the velocity of A with respect to B is 4 meters per second. C is running towards B in the other direction, and so VCB will be minus something. Well, let's say it's 5 meters per second. That's minus 5 meters per second. And now if you were to ask, what is the velocity of A as observed by C? Well, that'll be 9 meters per second. So the velocity of A with respect to C is this. The velocity of C with respect to A is minus 9 meters per second. Now, obviously, all this has been done assuming that B is at rest, that she is standing still on the ground. Of course, B is not really at rest. She is moving with the ground, and the ground on this rotating Earth is actually moving close to something like 1,000 kilometers per hour. That's faster than an average aircraft flies. Well, we know it's even more complicated than that because the Earth rotates on an axis that wobbles in space, and the wobbling Earth goes around the Sun at a fantastic speed of something like 30 kilometers per second. And of course, our solar system is just a tiny speck in the Milky Way, probably somewhere over here, and there are billions of stars that rotate around the center of the Milky Way. Our Milky Way is just one of the billions of galaxies which are moving apart from each other at some ferocious speed. And so, all motion is relative. There is no point in the universe which is at absolute rest. Relativity requires an understanding of what is space. Now that's a very hard question. I will take the easy way out and say space is where you can put objects. Objects like, for example, this book. Now this could be a small book or a big book, in which case we need to know how to measure lengths. If we can measure lengths, then we can measure areas and volumes. And length can be measured with a ruler or a meter rod. In this way, we can know whether a pencil is short or whether it is long. And of course, if it's longer than 1 meter, then we can use a measuring tape. If it's longer than this measuring tape can measure, then we shall have to use other means. So if we want to find out the distance between the Earth and the Moon, we use radar. But we shall still measure that distance in meters or fractions thereof. So the point is, we know that space exists because we can put objects there, and we know how to measure lengths. As long as we can measure something, that's good enough for physics. But now let's come to what is time. Again, it's a very difficult philosophical issue, but for us, we will take a simple understanding of it. Time will be understood as a measure in which events can be ordered from the past through the present into the future. Now, let's take an example. Here's a batsman hits a ball. That's an event. It happened at some time. That ball was caught by a fielder. That's a second event. The third event is an appeal. And the fourth is its rejection by an umpire. So here we have a situation where T1 is when the ball was hit, T2 when it was caught, T3 when it was appealed, T4 when a no ball was declared. So T1 is less than T2, is less than T3, is less than T4. That's a sequence of events that's telling us the direction of increasing time. We need to be able to measure the time between events. Here's one possible way. Sand is placed in an hourglass. It runs from the top to the bottom. And when that happens, you flip it around. It takes almost the same time to go from top to the bottom again. It's not a very good way because the sand runs at a rate that depends upon the outside temperature and upon the graininess of the sand, which changes over time. Here's a better way. This is a clock wound with a spring, and it has a pendulum whose length determines how long it takes to swing from one position back to itself. It's not perfect, but it's better than the sand glass. However, it too suffers from the fact that with age and with changing temperatures, its accuracy decreases. A much better clock is a natural one. It takes 365 days, 5 hours, 48 minutes and 46 seconds for the Earth to complete one full revolution around the Sun. Here's another kind of clock. I'll call it a light clock. Imagine two mirrors. A particle of light, that is a photon, is emitted from the bottom, goes to the top, is reflected, and is constantly shuttling back and forth. Now, if we know the distance between these two mirrors very accurately, and we know the speed of light, then we'll know how many times in a second this photon oscillates between the top and the bottom mirrors. In fact, this kind of clock can now be put on a chip, and these days atomic clocks are the most accurate of all clocks. Using an atomic clock, we can actually see that the Earth is slowing down as it rotates about its axis. In fact, in every century, the length of a day is increasing by 1.7 milliseconds. That is to say, 1.7 thousandths of a second. Now that we've understood the meaning of space and the meaning of time and have learned how the two are measured, we're going to move on to space-time. This involves putting space and time together. Look at this axis over here. That's the position axis. Here is the time axis. And now let's suppose that an event happens. Well, this event has happened at some time, let's call that t, and at some position, x. I'm just taking one dimension. We can go to 2 and 3 later. So this distance is x, that is to say from here till here, and this time is t. So this single point over here, this event, is the point t and x. Now, imagine there's a point over here, over here, over here. We can put an infinite number of such points, And the collection of all such points is called space-time. Let's suppose there are two events that happen. So the first event happens here. Let's call that the event A. This is where the event A happened. So the position is on this line, and this is the time on which the event A happened, and that's this line. There's a second event. Let's call that B. And so this is where the event happened. This is when the event happened. We could call this event T1 X1, and we could call this event T2 X2. Let's say that instead of one direction, we had two directions. So here is the x-axis, here is the y-axis, and here's the time axis. Now this event over here is defined by three numbers, t, x, and y. While we are all capable of understanding three dimensions, and there are three dimensions because there's t, x, and y, three numbers. However, we humans are not equipped for dealing with four dimensions. But there's no difficulty. There's an event that happens at some time and some point in three-dimensional space. So t, x, y, z, these define a point in space-time of four dimensions. And let's say we call this the point P in space-time. So four-dimensional space-time is going to be the collection of all different points P. Even though we can't imagine this, nevertheless we have no difficulty in dealing with it mathematically. And of course you could go from 4 to 5 to 6 to any number of dimensions. It's not necessary to be able to imagine four-dimensional space-time, but if you really want to, think of it as a three-dimensional grid with a clock at every point in space. Let's see what the motion of a particle looks like in space-time. Just to make things simple, I'm going to take only one dimension of space. So there's a particle that can move towards the right or towards the left. It has position x, and here is the time axis. So imagine that there is a particle which is at rest. That means that at time t equal to 0, it was over here. At a later time it was here, and a still later time it was here. Far back in the past and far into the future, it is at the same position. We call this the whirl line of the particle. Now, imagine that this particle was actually moving. In that case, as time increases, it is moving further and further to the right. So its whirl line is now this over here. If it was moving towards the left, then its whirl line would be like this, moving towards the left. Now let's consider a particle that is changing its speed with time. So if it started off at the origin over here, then let's say it stayed at rest, it moved towards the right, and then changed directions, and then went towards the left, came back, and so forth. So this whirl line over here is that of a particle which is changing its speed. Now let's look at the whirl line of a photon, a particle of light. As you know, the fastest moving particle is a photon. Nothing moves faster than light so far as we know. Suppose this photon is created at this point and it is absorbed at this point. Then this is the first event, this is the second event. I've plotted over here the distance as a function of time. Time is measured in seconds. The distance we shall measure in light seconds, meaning that this is the distance which is covered by light in 1 second. Let's say we put 1 second of time over here, then this is 1 unit of distance. That is the distance light will cover in 1 second, here 2 seconds, and so forth. In which case, you can easily see that this whirl line is tilted at an angle of 45 degrees. Let me repeat that nothing can travel faster than light. So now let's look at this diagram over here, which is called a light cone. Here is an event that happens at the origin. So at position equal to 0, at time equal to 0, the light will move out along this 45-degree line, this way and that way. So this is light that is moving towards the right. This is light that is moving towards the left. And of course, if there are 2 dimensions, then there is, we could over here draw a set of axes that look like this. Then imagine connecting up all the points over here. We'd call this the future light cone, and down here the past light cone, which looks like this. Now, the fact that nothing can travel faster than the speed of light means that if there is a particle over here, then in a certain amount of time it has got over here, but light has gotten much further. It's gotten here. So all events that lie within this future light cone are those events which could possibly be connected by a ray of light that started from the origin over here. We call them causally connected events. That means that this event over here could have been influenced by this, but this event, that is to say this point in space-time, Q, cannot be connected with the origin. It is called causally disconnected. That's because nothing can travel faster than the speed of light, and so this event over here could not have been influenced by the earlier event here. In turn, what happened over here at P could have been influenced by events that lie in the past light cone. But no event like this one over here could have influenced what happens here. We'll now come to the concept of an inertial reference frame. Very simply, an inertial frame is one that is not accelerating. So, if we have a point, or let's say a material particle, which is here, we can locate it with the help of a coordinate system or a frame S, and that has X, Y, and Z axes. This is not an event. I'm merely locating a point in three-dimensional space. So we go a distance X in this direction, a distance Y in this direction, and a distance Z in this direction. Now, how do I know that this is an inertial frame? Well, that's because if this particle is placed here, it'll stay here. It will not move off by itself. Of course, there are many inertial frames that are possible, and each one can be identified by the fact that a particle placed at rest will remain at rest. Now, here's a real-life example of an inertial frame. There is this truck standing at rest, with respect to the ground, of course. The boy throws a ball, it goes up, and then it comes back into his hand. Now, suppose that this truck is moving towards the right at a constant speed. This boy throws the ball vertically upwards, according to him, and he notices that after a while it comes back into his hand. So as far as the boy is concerned, there is no difference between this situation and this situation. On the other hand, a man who is sitting on the ground over here will see the ball go along a trajectory which is a parabola. When a body is placed in an inertial frame and no other forces act upon it, then it stays at rest. But when there is acceleration, meaning a non-inertial frame, then an apparent force acts upon that body. So look at this pulley. As the platform rotates, apparently there is a force acting upon it, and that causes the string to stretch. It's clear that this is an effect of rotation, and it's clear that we can always tell a non-inertial frame from an inertial frame. Now let's imagine that there are two inertial frames and an event happens. How is this to be described in one frame and in the other frame? Let's call one frame S and the other frame S prime. In S, we measure distance along the X, Y, and Z axes. In S prime, along the X prime, Y prime, and Z prime axes. The frame S prime is moving towards the right at a speed, let's call it v. And now, imagine that an event happens. Now, in S prime, it will be described as having occurred at time t prime, position x prime, y prime, z prime. And in S, that event will be described as having occurred at time t at positions x, y, z. Now, of course, if there is one universal time, as Newton and Galileo believed there was, then there is no difference between t and t prime. So t prime is equal to t. But now let's look at this diagram. This distance from here to here, which is x, is equal to vt plus x prime. And so therefore, x prime, that is to say this distance here, is equal to x minus vt. And of course, looking at this diagram, y prime is the same as y and z prime is the same as z. Now, this over here is what is called the Galilean transformation between the frames S and S prime. Now, imagine that this was a particle, and so it's here right now. In a little while, it'll be, let's say, over here. So it has changed its x, y, and z coordinates in a certain amount of time. Or you could say it's changed its x prime, y prime, and z prime coordinates in that same amount of time. Well, we know how to get velocities. Let's just take dx prime by dt. And this from here is dx by dt minus v. What does that tell us? That the speed that is observed in the S prime frame, let's call that ux prime, that's equal to the speed observed in the S frame minus v. And so we have a relation between the speed observed in the S prime frame and the S frame. Of course, we can do it for all the others over here. We'd just find uy prime equals uy and uz prime equals uz. And that's, of course, because there's no motion along the y or the z axis. We could even get the accelerations. We have d2x prime by dt squared. That's the acceleration in the S prime frame. Well, that's dx by dt differentiated, so that's d2x by dt squared. The derivative of v is 0 because this is an inertial frame. And so the accelerations observed in the S prime frame and the S frame are exactly the same. So we could write ax prime is equal to ax, and of course then ay prime is ay and az prime is az, and so forth. Now, of course, for this very simple situation, there is only this one equation which is of any real significance. We can write it as ux is equal to ux prime plus v. And you can understand that very well, because if there's a particle that's moving, let's say, towards the right like this at some speed ux prime, that is observed in s prime, then there'll be an additional v which will be seen by the observer who's stationed in the inertial frame s. Obviously, if s prime is the frame that is attached to a car moving towards the right at 30 kilometers per hour, and you throw a ball forward at 10 kilometers per hour, then the speed that will be observed in s will be 30 plus 10, 40 kilometers per hour. Let's apply what we've learned so far about Galilean transformations to sound. Sound, as you know, is vibrations in the air or any fluid. Now imagine that there's a source of sound, and this source puts out very sharp pulses of sound which then travel towards this boy. This boy is going to see the speed of the pulses approaching him at about 330 meters per second. But suppose there was this woman who was running towards that same source. She would see the speed of sound as being 330 meters per second added to her speed, which is 10 meters per second. And so she will see 340 meters per second. On the other hand, after she has passed by that source, she will see the speed of sound as being less, as 330 minus 10 meters per second. And if she was running at the speed of sound, well then the pulses that come out of here would never be able to catch up with her. Now all this assumes that there is a medium, and that medium is the air. The pulses of sound travel in that medium. Let's now use the same logic of Galilean transformations but apply it to light. So, imagine that there's a source of light that's putting out very sharp pulses. Those pulses are now traveling towards this boy. He will see the speed of the light pulses approaching him as this very large number, something like 3 times 10 to the power 8 meters per second. On the other hand, if there's this woman who's running towards this source of light, she, by this logic, will see the pulses approach her at 10 meters per second more than this boy observes. And if she's running away, then she will measure the pulses as 10 meters per second less than this boy. And now here we are assuming that there's some kind of medium filling space, and it is in that medium that the light is traveling. So clearly, light has different properties in different inertial frames by this logic. Now this is precisely the logic that Einstein did not accept, because it would require electromagnetism to have different laws in different inertial frames. And so this situation over here is something that Einstein certainly would say is wrong. In other words, the use of Galilean transformations for light is wrong. Now, if there is some medium through which light needs to travel, where is that medium and how could one find it? Let's say that all of space is filled with this medium. Call it the ether. This mysterious fluid clearly had to be transparent and should offer no resistance to the movement of bodies through it, in particular that of the earth. Now let's assume that this ether is at rest with respect to the universe, and that the sun is at rest with respect to the ether. But as the earth goes around the sun, then it will have to move through the ether, and therefore there will be what you could say is an ether wind. You see that now the earth is moving in this direction, and so there's an ether wind directed oppositely. But here, the Earth is moving in this direction, and so the ether wind is directed oppositely. But we know that the speed of the Earth, which is fairly large, 30 kilometers per second, is actually much smaller, 10,000 times smaller than the speed of light. The smallness of this effect meant that the experimentalists who looked for it had to be very clever. Here is how they did it. Here is their apparatus with a light source, a mirror over here, a mirror over here, and a beam splitter, which is a partially silvered mirror. So if a beam of light comes and hits this beam splitter, part of it will go through, part of it will be reflected, and then after reflection, this is going to come back and come hit the screen. Similarly, part of the light from this mirror is going to come back and hit the screen. Now, let's assume that the Earth is at rest. That's wrong, but let's see what happens then. In which case, the amount of time that will be taken to go from here to the mirror will be L over C, and so the time taken, let's call it the vertical time, for the light to go and to come back will be 2L divided by C. Of course, the same amount of time will be taken for the light to go this way and to come back here. So, assuming that this has put out a very sharp pulse of light, both pulses, that is to say, the part which went here and came back and the part which went here and came back, will arrive at exactly the same time, and then they will be diverted here onto the screen, and they will double in strength or amplitude. The vertical time was this, the horizontal time I'm going to write is exactly the same, 2L over C. Again, all this assumed that this apparatus was at rest with respect to this gray stuff over here, which is supposed to be the ether. Now we'll take the Earth to be moving through the ether. So there is an ether wind that is directed this way with speed v. And now let's consider this apparatus as it moves through the ether. So everything's moving, the light source, the beam splitter, the mirror, the screen, and so forth. Now after a little while, this mirror will have moved here, and let's ask how much is the time taken now for the light that is sent off by this beam splitter to this mirror and for it to come back. Well, let's make a little diagram of that. So this is the length L. In a certain amount of time, let's call it T1, it has moved off a distance VT1. So the distance from here till here is VT1. Then in that case, this distance over here will be, of course, the square root of L squared plus V squared T1 squared. And the amount of time, T1, is then this distance, which is square root of L squared plus V squared T1 squared, divided by the speed of light, c. Now let's square both sides. Take the c over here, so you get c squared T1 squared equals L squared plus V squared T1 squared, and that gives us T1 equals L divided by square root of c squared minus V squared, and let's write that as L over c into 1 over square root of 1 minus V squared divided by c squared. That's the time taken for the light to go from here to here, and of course there's an equal amount of time that's needed for it to come back here. So the vertical time, let's call that TV again, will be 2L over c. That's the factor we had before for the stationary Earth, multiplied by this factor, 1 minus V squared divided by c squared. Let's do the same calculation for the light that is emitted horizontally. So we're looking at this point over here. What happens is that as soon as the light is emitted from this point, it starts moving towards the mirror, the horizontal mirror, but in a small amount of time, this has moved a distance over here. Let's call that VT1. Okay, so that means that this light has to travel a longer distance because this mirror has moved off an extra distance V times T1. And so therefore the time taken, T1, will be equal to this distance, which is L, plus this distance, which is VT1. So that total distance to be traversed is L plus VT1, and then to get the time, that's the distance divided by the speed, and from here we get the going time, that is to say the time to go from here to here, that T1, now we can take C over here, and so this will become simply L over C minus V. Now when the light from this beam splitter has arrived over here, it's going to go back and enter the beam splitter, but the beam splitter has moved a certain distance. Let's now look at it this way. So here is the mirror, here is where the beam splitter used to be, but now it's moved off a certain distance, let's call that VT2, and so the light that goes from here has to travel a lesser distance. Calculate the time, let's call that T2. T2 will be then L minus VT2 divided by C. So from here, taking C on that side, we get T2 is L over C plus V. And so now let's, I'm running out of space, but let's write the horizontal answer. That is L divided by C minus V. That's this over here, T1, plus L divided by C plus V. And that is equal to 2L, you can just check this, 2L over C into 1 over 1 minus V squared divided by C squared. Now let me quickly recapitulate. So here was the light which was moving this way. It had to travel to a mirror that was running away from it and therefore had to travel a distance L plus VT1. On the way back, it was traveling this way, but now the beam splitter had moved forward in that time because the whole apparatus is moving forward, and we called that distance VT2. So finally we got the horizontal time, which is this, and the vertical time, which is this. So compare the vertical time, which has got 1 over square root of 1 minus V squared over C squared, with the horizontal time, which has got 1 over 1 minus V squared over C squared, no square root over here. That says that the light which travels this path and the light which travels this path are going to enter the screen over here at slightly different times. In other words, there will be interference between these two, which will be destructive in some places and constructive in others. Now, all this assumed that there was an ether wind. So did Michelson and Morley find any evidence of the ether wind? Did they find destructive and constructive fringes on the screen over here? The answer is no. The failure of the Michelson-Morley experiment to establish the existence of an ether meant that light did not really need a medium in which to travel. And this led Einstein to formulate two revolutionary new postulates or assumptions that are the basis of the theory of special relativity, and we'll come to them in the next lecture.